Hi, this is project submission for dundyHAcks hackathon. We are from India, representing Indian Institute of Technology, Madras. Myself being Harshinan and my teammate is Ashwini Nair. Our project is in the field of mobile robotics control system. We tried and succeeded in minimizing the human factor involved for tuning the gain of nonlinear model predictive control system using genetic algorithms. Nonlinear MPCs being the heavyweight champions among all the industrial grade control systems, if tuned perfectly, yields exceptional results, but the optimization being a crucial part requires an expertise in experience. So our project replaces human expertise with genetic algorithms, yielding a good performance. Our approach was to track trajectory of a differential drive robotic system based on the parameters like velocity, acceleration, omega, yaw moment, etc., setting optimal limits on velocity and omega. So we are going through the readme file of our project. So you can see. So this is the workflow. This is the workflow of nonlinear model predictive control system for rate differential drive. So here the MPC has a lot of options. Initially we set the reference for the point and the track for the model to travel through, and MPC calculates all the future paths which it has, and it chooses the fittest path, that is the path having least cost of travel. The cost of travel is in the terms of linear and rotational kinetic energy and limits on acceleration and omega. Thus, the MPC outputs variable required for the planned model, which being a differential equation outputs the next position. The state estimator works on the feedback loop for position, which can be varying according to the external factors. So as we move on, you can see this is the planned model, and the variables and the errors are as shown in the figure. So as we go on, this is the dynamic equations describing the planned model, and these are the constraints, and this is the cost function. So here we are running the program now. As you can see, the genetic algorithm is used to calculate all the weights in the cost function, and now it is running generation 1. That each individual in the generation is a weight of 7 weights. So the rest parameters of the genetic algorithm are as shown. So here we have a population of 20 and a maximum generation of 100. So it will be taking some time. So as we go, we see the MPC runs each individual 300 times and records the performance of best performing individual in each generation in a JSON file. So the performance of the model using the genetic algorithm is based on the evaluation of a fitness function. The fitness function is as shown here. So the performance of each individual is based on this fitness function. The fitness function can be improved on based on the interactive decision tree, and interactive decision tree evaluates the performance of best individual among each generation based on the user's response of improvement. The performance can be improved up to the user's satisfaction. So here we see the generation 2 is running currently. So in interactive decision tree, it starts from a uniformly distributed weight for calculating improvement of each generation of genetic algorithm. The program improves the weakly improved matrices and can be terminated on reaching a satisfactory level. So here you see the generation 2 is over, and now the interactive decision tree is comparing the best individual from generation 1 and generation 2, and it shows that. So here you see the comparison shows that there is no significant improvement in generation 1 and generation 2, and if at all we had, we could say that we want improvement in which values. So at this position I want to improve all the values, so I type in all the 5 values and I say I want to improve 1, 2, 3, 4 and 5, and it again runs the genetic algorithm for generation 3, increasing the weights of this fitness function. So as we move on, we could see this goes on running. So this is the result from the previous run. So here we see the generation 1, and the trajectory information graph shows the path planned by MPC based on the random weights, which will be improved in the next upcoming generations. The second graph shows error at each positions. The red line in the first graph is a planned trajectory which can be looked upon to evaluate the performance. As we move on to the next graphs, as we see, if we reach generation 20, there is a significant improvement. As we move on in the generation 40, there is more improvement. As we go on to 60 and 80 to 100, here in the 100th generation, we get the optimal values of the weights which can be used for the MPC algorithm to maximize the performance in current model. So finally, if we had a bit more time, we could have completed the Simulink model for a nonlinear MPC algorithm according to our workflow, which could be used to evaluate the performance in variety of tracks, and we could show our model being the best performing model. So at finally, thanking dundyHAcks to give us the opportunity.